In this presentation, we'll briefly discuss how fluids under pressure are controlled. Fluids under pressure are dangerous and must be controlled in order to work safely and accomplish useful work. Pressure, direction, and flow are quantities that must be controlled, and valves are used to do this. Valves may be connected to machinery in one of two ways. Valves may be connected by mounting them on a machine base called a manifold, as in the illustration on the left. O-rings are caught and pressed between the ports of the plate and the valve to make the seal once cap screws have been installed and torqued to specification. Another method of connecting valves, and less common in factories, is pipe mounting. With pipe mounting, threads are made into the ports and connectors are threaded into place to complete the connections. We will discuss threaded connectors in a more detailed explanation in a later lesson. This illustration shows how a simple pressure control valve with an internal movable member provides a path for oil to get back to tank when the pressure reaches a predetermined limit. The most common method involves the use of a spring to bias the movable member to the blocking position, and as pressure increases, allow the spring to be compressed as the movable member is pushed against the spring by the force of fluid. In this way, the relief valve acts similar to a voltage regulator, regulating pressure based on system demands. We will study two different design types in detail later in this course. In a pneumatic system, control of pressure happens at 2 points. First, pressure at the receiver tank must be limited to prevent rupture of the tank, but also to create the potential for the air to move downstream to the point of operation. In other words, the pressure at the receiver tank is usually the highest of the system. The second place where air pressure must be controlled is at the point of operation. At the receiver tank, a pressure switch is commonly used to turn off electrical power to the prime mover. There are other methods to control receiver tank pressure, but we will not discuss them in this lesson. A pressure switch uses contacts to channel electrical energy to the prime mover. Second, downstream, a pressure regulator is used to reduce the pressure to the usable level of the actuator located at the point of operation. Mechanical pressure switches use a flexible device called a bellows to push against a spring, which in turn allows contacts to open and stop electricity from getting to the prime mover, which is usually an electric motor. There is a built-in range differential which controls the cut-out, cut-in pressures to ensure the pressure does not fall below the working requirements of the system and its equipment. Adjusted by the manufacturer, these switches rarely need any maintenance, and often the compressor fails before the switch does. The safety relief valve protects the receiver tank from rupture in the event that the pressure switch should fail to stop the electric motor. This is rare, but it does happen. The safety relief valve is also known as a pop-off valve. They cannot be adjusted, and if replaced, must be matched by flow and pressure capability. The port to which this valve is connected should never be plugged. The pressure regulator is a normally open or passing valve which closes when downstream pressure reaches the tension of its spring. Tension on the spring is adjusted by the control knob or T-knob. When set pressure is reached, the diaphragm pushes against the spring, causing it to compress. Then the stem moves upward, which forces the poppet in the path of air, restricting it. If downstream pressure raises above upstream, the valve will release it into the atmosphere. When excess pressure is released, air moves through the tiny opening in the secondary port, lifting the diaphragm off the top of the stem and allowing air to escape through a tiny hole in the upper housing. There are a number of different design types of directional control valves that we'll call DCVs for short. This one is a spool type and meant to represent a valve used in hydraulic systems. The spool fits within the body of the valve and moves back and forth, blocking some passages and opening others. Fluid from the pressure port P is directed toward the actuator port A when the spool shifts to the left, and to the actuator port B when it shifts to the right. Flow control valves are used to adjust fluid movement in fluid power systems. A needle valve is a basic means of controlling fluid movement by restriction. Similar to an adjustable resistor used in electrical circuitry, a flow control reduces flow rate with a reduced opening. The type shown is an adjustable needle valve. The needle valve will meter flow in both directions. The schematic symbol for an adjustable flow control is shown by the two curved lines and an arrow. The placement of the arrow emblem in this symbol, as well as others, indicates that something is adjustable in the component which the symbol represents. Generally, the term flow control refers specifically to a device designed for controlling flow by applying resistance and includes a needle valve and a check valve within the same body, although a needle valve and a check valve in single separate bodies are used in industry. Secondly, in this course, we often speak of the topic of flow control as distinct from the device of the same name. By comparison, a flow control does the same thing as a resistor in electrical circuits. A type of non-adjustable flow control is an orifice. It is usually described as a tiny opening in the path of fluid. The orifice is fixed and cannot be adjusted. Its schematic symbol is on the right side. A needle valve is comparable to a variable resistor, and a flow control is comparable to a variable resistor with a diode. There are many types of adjustable flow controls used for controlling different kinds of fluids, but they are not all suitable for use in hydraulic and pneumatic systems. The globe valve on the far left is obstructive to flow. The gate valve in the middle is obstructive to flow and will leak if mid-positioned. The ball valve is not used for flow control, but is often used as an on-off valve for controlling flow. The primary influence on actuator speed is flow rate. Flow rate is the quantifiable measure of moving fluid. Maximum possible flow rate is limited to the physical size of the flow generator, whether a pump or a compressor. To begin with, there's a mistake in this schematic regarding pressure. I use this to test the understanding of my students. Pressure is the influence or push that causes a fluid to move. It's similar to EMF in electricity. While fluid is in movement, there exists a difference in pressure, otherwise there would be no movement of the fluid. While the schematic shows a change in flow rate, it fails to show a corresponding change in pressure. If the pressure is 500 at the relief valve and 500 at the needle valve, the fluid is static and there can be no movement of the actuator. In order for fluid to move, there must be some difference in pressure. The needle valve was meant to show that as flow is reduced going to the actuator, the remainder must go over the relief valve to the reservoir or the tank. So the relief valve here is shown as activated. This is for illustrative purposes only, because this is never the case on an industrial schematic diagram. As mentioned earlier, the symbol for a fixed restrictor or orifice communicates a flow control that cannot be adjusted. There are a variety of ways this may be accomplished. Even something as simple as a pipe plug with a hole drilled into it could be a fixed flow control. The non-pressure differential mistake of a previous slide remains. The purpose of this slide is to demonstrate that the speed of an actuator may be calculated. The measurement is a combination of speed in seconds or minutes and distance, which could be in feet, inches, meters, and centimeters. In this case, the measurement is the speed of the cylinder rod in feet per minute. The majority of my demonstration calculations, however, will be in units of inches per minute. Note that the relief valve here is shown as activated. This is for illustrative purposes only, because this is never done in the case of an industrial schematic diagram. This is an example of how to calculate cylinder rod speed. The math requires that you place the correct numbers in sequence using a calculator. The most important thing is the relationship between the quantities. Rod speed means the speed at which the cylinder rod is moving in units of distance and time. If calculating rod speed in inches per minute, place the given units into the calculator as shown. GPM is gallons per minute. GPM may mean the flow rating of the pump, or it can be made up for the purpose of predicting speed. The area is calculated by taking the diameter of the cylinder bore and multiplying it by itself and then by 0.7854. The area can also be given as in the case on the next slide. For demonstrative purposes, we will assume the flow rate is correct on this slide. The cylinder rod moves at a speed which is controlled by the amount of oil coming from the hydraulic pump and limited by the restriction of the flow control. If 4 GPM go to the cylinder, the remaining 1 GPM must go back to tank. The area is given in this case and does not need to be calculated because it has already been given in the correct units. The formula is GPM times 19.25 divided by piston area. You will often find the answer has been rounded as it has been here. Remember, the relief valve here is shown as activated. This is for illustrative purposes only, because this is never the case on an industrial schematic diagram. This slide shows what happens to pressure and flow upstream when there is an increase of resistance. The needle valve and load affect the reading on the upstream pressure gauge. If the needle valve's opening is reduced further, it stands to reason that the pressure at this point will increase and flow across the needle valve will decrease. As the opening of the needle valve is reduced further, the flow reduces in direct proportion. This is very easy to demonstrate on the training equipment. Note that, as in previous slides, the relief valve here is shown activated. This is for illustrative purposes only and is never the case on an industrial schematic diagram. This illustration shows two pressure gauges in the same line with a restrictor between them. The difference between the gauges, or delta P, will depend on the size of the opening, the pressure on the left, which is upstream, and the pressure on the right, which is downstream and presumed to be caused by the load. In general, if the gauges read a difference, there is flow. If the gauges read the same, Pascal's law applies and it is understood that there is no flow. If pressure working on a fluid is increased, the fluid tends to move faster or in greater volume. So, squeezing a bottle of toothpaste increases the pressure on the fluid, and standing on an air mattress increases the pressure on the air. In both cases, the fluid moves faster with the increase of pressure. This is what two gauges might read with a needle valve placed between them. As you can see, the difference is affected by the needle valve. It should be understood that the needle valve will affect flow in both directions. We will see this example when we set up our equipment in the lab. Once the needle valve has been set, an increase of pressure at the relief valve will force more oil across the needle valve. This is like using a variable power supply in electricity to increase voltage over a resistor. This effect will be demonstrated in the lab. As I mentioned before, the load on the actuator will also affect pressure differential. The more load applied, the more pressure is applied by the relief valve to overcome the load. If the load exceeds the potential of the relief valve, the cylinder stops. As the load increases, the flow going to the actuator decreases, sending the remaining flow over the relief valve back to tank. Students will get to see this when they use a device called the load sleeve during an experiment in the lab. Note the vertical arrow in the symbol. This symbol is that of a pressure compensated flow control valve used in hydraulic systems to keep flow constant regardless of load. It does, however, have limitations. The maximum load must be no more than 100 psi below the relief valve setting. This device will be demonstrated in our lab. There are two common types of pressure compensated flow control valves: bypass and restrictor. The one used on our equipment is the restrictor type. In this slide we see the floating spool of a restrictor type pressure compensated flow control valve. The spool slides from one side to the other, either closing off the passage or opening it based on pressure differential, mainly pressure caused by the load. When load is light, the valve restricts, and when load is high, the valve opens to allow more oil to go through. These kinds of valves do not exist in pneumatics and are becoming rare in hydraulic systems because of the advancement in electronic control systems. This is what a circuit would look like with a pressure compensated flow control valve. The rate of the cylinder speed is set with the adjustment knob. As the load increases, the differential remains the same across the PC flow control valve. The load can increase up to 400 psi before the cylinder will slow down. In this configuration, the pressure compensated flow control valve only affects flow in one direction. If it were placed in the main line ahead of the DCV, it would affect flow in both directions of the actuator. This information has already been explained, but the relief valve is the voltage regulator of the hydraulic system. It brings to point an important advantage that fluid power systems have over electrical systems. If the demand for pressure of the load exceeds the limit of the relief valve, the cylinder will stall out. If this were a hydraulic motor instead of a cylinder and an overload was applied, the motor would simply stop. If you did this to an electric motor, the overloads would trip or the motor would simply burn up. As oil becomes heated, its flow characteristics change. To keep oil stable at operating temperatures, oil manufacturers put additives into the oil. Even with additives, oil viscosity tends to change with temperature, and this could become a problem affecting hydraulic machinery speed. When oil heats up, it thins out and tends to move faster through a system. If this could be eliminated, it would keep the machine operating stable regardless of temperature change. There are two types of temperature compensated flow control valves. This one uses an aluminum needle valve which contracts when cold and expands when hot. If the oil is thick because it is cold, the needle valve retracts and this allows more oil to go through. Likewise, if the oil becomes hot, which means it thins out, the needle valve expands and restricts the oil passage. In this way, a valve of this type prevents a speed change in machine operation caused by an increase of temperature. This type of temperature compensated flow control valve is called a sharp edge orifice. When discussed in certain textbooks, the writers state they do not fully understand how it works. However, once adjusted, this valve ignores changes in viscosity caused by temperature increases and keeps oil flow constant. This schematic symbol shows a flow control with a combination of pressure and temperature compensation. This is an older style drawing of a hydraulic system called a pictorial or double line drawing. They are rarely used in industry today, but they do have some educational value because of their picture-like appearance. Likewise, this is an older style drawing of a pneumatic system called a pictorial or a double line drawing. We don't use these very much at all today, but from time to time and for educational purposes, their pictures do help in explaining some of the components in the system. This is a schematic drawing, also known as a single line drawing, of a hydraulic system. They read faster than any other types of drawings once the meaning and purpose of the symbols is known. The manner of reading is to identify the power unit on the left and then to trace the path of oil flow out into the system toward the actuator. This schematic drawing is a pneumatic system. To begin reading, identify the power unit on the left and then trace the path of airflow out into the system toward the actuator. The connection of the line at the top of the receiver tank is no longer used and is supposed to enter the tank from the left side, maintaining parallel symmetry with the outgoing line on the right. This is a sample list of some older style hydraulic schematic symbols and their corresponding double-line renderings. This is a sample list of some older style pneumatic schematic symbols and their corresponding double-line renderings.